Swayam Prabha. Digital India. Educated India.
First, let us look at what additional changes or the network transitions that happened with the widespread adoption of the Internet. Foremost is the rise of the middle boxes. The phrase middle box was coined by Lixia Zhang, a computer science professor from UCLA. It was termed as a graphic description of a phenomena that stormed the Internet in the early 90s. By definition, a middle box is an intermediary device that is placed on the datagram path between the source host and the destination host, and by functionality, they perform the functions other than the normals or the standard functions of an IP router. And these are also known as the network appliances when they are purpose-built hardwares, or by the term network functions, or more recently, the virtualized network functions. And traditionally, these middle boxes were deployed in communication service provider networks for various purposes. For example, in the early 90s, when the Internet community sensed the end of IPv4 address space and needed newer alternatives to keep up or meet the scale and growth of the Internet, many interim solutions were sought. And as an interim solution, the networking community came up with a gateway-based address translation services encompassing public and private addresses. And this resulted in what we started to see as the rise of the network address translators for the IPv4 case. And as the things progressed and IPv6 was proposed as a full-fledged solution, still the usage of the network address and protocol translators or the NAPT devices started to emerge. Now, when you look at these devices are transparent to the host on either end, that is both the source host and the destination host, but they would translate the IP address of an incoming packet from a private to the public address and route it out. So these kind of functionalities now that were built into the networks is what we refer as the middle boxes. And typically when the NAT or the NAPT devices were built, they were part of the gateway devices, but they could also be custom proprietary built devices as well. So in essence, these middle boxes are employed to provide basic in-network services like NAT, and we can even consider the load balancers, the proxies, and the transcoders as specific in-network services that these middle boxes provide. And second, with the need to enhance the security, several of the other kinds of middle boxes started to emerge, like the firewalls that are deployed at the periphery of a typical enterprise network or the campus networks, and the DDoS protection devices or the IDS or the intrusion detection systems or the intrusion prevention systems that are built for protecting the network from malicious packets. And these kind of security-oriented services also started to emerge, and we start to see the second phase of the middle boxes that were deployed. And more so, there is also another set of middle boxes, like the performance enrichment or the value-added service category of these middle boxes. For example, the WAN accelerators enabled to perform the TCP accelerations or the HTTP accelerations that you would need when you want to communicate across WAN, and also like the ad insertions that are typically used to introduce the ads that you typically see when you browse specific sites. So all of these kinds of different devices started to emerge, and what led to the rise of the middle boxes. And these middle boxes, be it the campus networks or the enterprise network, or even in the internet service provider or the ISP networks and telecommunication networks, and likewise in the data centers, all began to flood with the use of these various kind of middle boxes. And a survey was conducted by a team in UC Berkeley around 2012 on the deployment of middle boxes in the North American Network Operators Group that constituted of around 57 network operators. And the graph that I'm showing here presents exactly the results of what they observed. And to quickly summarize the plot here, what they tried to do is compare different network operators in terms and categorize them in terms of the number of hosts that they had into large, small, and medium-sized network centers. And based on the number of hosts that they host, the red here corresponds to a large scale, while the purple here corresponds to a small scale, and the two green and the blue here are the intermediaries or the mid-scale network operator centers. And what they saw in each of these cases was in terms of the number of middle boxes that they employed versus the number of the layer 2 switches and the layer 3 routers that those networks had. And invariably, we can see that on the right here, the portion depicting the number of middle boxes that were present in each of the network operators group, in each case, you can see they correspond almost alike to the number of L3 routers and the L2 switches that you see on each of these networks. So this indicates the widespread usage of the middle boxes that had already spanned several network operators. And if we dig at just one of the network operators case, a medium-sized network operators case, what they saw is the type of the appliances or these middle boxes that were used were for various purposes. Those included the firewalls, the network intrusion detections, the media gateways, the load balancers, the proxies, and so on. And the numbers you could see is almost on the orders of the total number of routers or the typical network elements that we expect to operate at layer 3 or the layer 3 routers. The numbers were almost the same. And this rise of the middle boxes was also studied in other ISP and data center networks, and the numbers were found to be in similar orders. So the survey, in a way, highlights the dominance and importance of middle boxes in different enterprise networks and how they started to shape the internet. So, in a way, the rise of the middle boxes and the emergence had significant impact on the internet architecture and the design principles that we discussed earlier. Unlike the traditional end-to-end principle, now with the middle boxes, instead of concentrating the diversity and functionalities at just the end hosts, these middle boxes tried to take and spread these functions within the network. And this was seen throughout the network as well. And besides the routing and forwarding tables that used to be maintained as the state necessary at the layer 2 switches and layer 3 routers, now these middle boxes also maintained a large number of state for different purposes. For example, if we consider the NAT device again, a NAT needs to maintain the address and port translation for each of the outgoing and incoming connections. So this, in essence, is a new state which is now becoming part of the network. And likewise, the load balancers, the reverse proxies also maintain the state mapping, the incoming connection to the mapped backend server, and so on. Hence, what we argued earlier, where the networks were just the dumb pipes, is no more true. And the networks are no more stateless, and we cannot consider the network anymore to be as dumb and could impact the way the networks operate. Further, now with the NAT again, we can see that the address transparency is completely broken. And as we discussed in the early internet principles that laid foundations by Vinton Cerf and Kahn's work, or what is also termed as a catenet concept, which is a concatenation of the networks to build the internet, which was based on a clear assumption that a single logical address space would cover the whole internet. But now with the NATs, this is no more true. And likewise with the emergence of the private network addresses, which basically is what the concept that the NATs use. And hence, what this meant is that packets essentially cannot anymore flow unaltered throughout the network. That is, given a source and destination address, these are no more to be considered as unique labels to route in the internet. And what you would need is basically the translations of these addresses to say how to route. And once the routing has certain endpoint, which is not exactly the endpoint as the host and hosts, but thereof you would change the addressing to route it in a private network. So we can clearly see that the end-to-end principle was almost violated with the rise of these middle boxes. Further, in the traditional internet architecture, we discussed earlier about the hourglass model, where the only box in the neck of the hourglass was the IP protocol, and hence the IP routers belonged to this neck. And their only function was to determine the routes and forward the packets, while also trying to update some necessary fields for the purpose of forwarding. Right? But now this is no more true with the middle boxes, because now the middle boxes can alter the entire packet's data structure and also occupy the same neck space as the IP routers. And this is where we start to observe the deviations in the hourglass model, as these middle boxes would perform functions other than just the IP forwarding. For example, a layer 3 load balancer or the layer 3 NAT that translates the addresses. And further, they are not just confined to layer 3 anymore. Although they reside in the network, they may operate at even higher layers, like layer 4, where they may even terminate a TCP connection, or even at layer 7, terminating an HTTP connection for the proxies typically do, and modify even the HTTP options and security parameters. So in one way, when we look at the middle boxes, they are a challenge to the hourglass model, as the middle boxes dilute the significance of IP as a single necessary feature of all communication sessions. Further, if we look at in another way, these middle boxes are a challenge to the transparency of the network layer and may break the network functionality independent of the end-to-end systems. Hence, when we considered the fate sharing principle earlier, we said that the failure or a success is a collective information that's because of the ends. But now, the systems may fail to operate not because of the ends, but because of the failure in the network for one of these middle box devices. So now it is no more okay to lose if any unrelated entity goes down while the end connections are still up. So having the stateful middle boxes, we end up violating this fate sharing principle. Again, for example, if we consider the NAT, if the NAT fails or the NAT device gets broken, then the connection between the two end hosts also gets broken, because there is no more a translator that can facilitate the routing within each of the private networks or provide the network as a proxy to the other side of the public network. And likewise, it would be with the load balancers and proxies. Hence, the fate sharing principle also is a deviation when it comes with the middle boxes. And moreover, as these middle boxes may transparently modify the state in the network packets, the end hosts may end up receiving completely different data at each layer than the one that was intended by the sender at the origin. What this means in another way is that we have violated the invariant principle that was the crux of the layering principle. Right? So overall, now this horizontal communication can no more guarantee this invariance. And thus, we start to see the deviations and the violations of majority of the internet architecture and design principles that we discussed before, because of the widespread proliferation of these middle boxes. Besides, we also need to consider, as the networks evolved, what other compromising changes occurred. And we can see that there were several compromising changes that made us drift from the initial principles of the networking. And for example, consider the success of TCP and the socket APIs. So at one end, the success of the web, the TCP IP, greatly helped scale to larger audience, bringing diverse networking services. But on the other end, it also started to ossify around the services started to ossify around this protocol stack. So what I mean by this is, when you see the widespread use of a specific protocol amongst the set of protocols, most of the services try to adapt towards the same protocol. And this, in a way, stifled the adoption of newer protocols and rather hardened the network stack, often resulting in just the adoption of the TCP over IP as a preferred protocol stack. The successful and widely adopted technologies started to pave assumptions about the underlying traffic. For example, now with the middle boxes on one end, and the middle boxes need to support the different protocols, it started to bring different aspects of how the monopoly over a specific protocols could occur at the network level. And there was a study that was done in the early 90s, and that was the KHARA traces, that showed that around 95% of the WAN bytes, or around 85% of the packets, were just TCP alone. In the sense that the various other protocols that corresponded to the transport layer were more or less getting neglected, or were not able to keep up with the traffic that we see because of the services hardening around the TCP IP stack. Also, the success of the socket APIs that provide the mapping of an application to the transport protocols, you could see that in most cases, the type of a socket that you would create would invariably map to TCP as its default transport protocol. And thus, we started to see this form of a hardening, and also called the ossification in this case. Moreover, this progression again also broke the end-to-end argument, like I said, because the network is no more dumb but an intelligent stateful pipe. And all these aspects, along with the success of the web, also started to shape what looks like the most preferred the network stack, and that looked like it would be HTTP at the application layer, TLS for the security, and TCP and IP. And most of the applications that built around would only part of the application stack would change, but most of the services, the other TLS, TCP, and IP would remain intact. And this was again the another form of an ossification that happened within the networks. So, internet now could no more be flexed, modified, or even experimented with. And especially if the data has to go through network being no more just a stateless pipe, but lots of interspersed middle boxes, whatever the protocols that middle boxes would support are the ones that would make it to the end host. And if there were protocols and the middle boxes in the path of the internet were not supporting them, then it's likely that the packets would get dropped at the middle boxes and your protocol would never make it to the other end. So all of these aspects tied with the commercial interests started to affect the way the internet research would progress. And typically you would have a lot of newer protocols that you would want to experiment with, but internet became resilient to all of these protocols that you would want to develop and deploy and try. And it was also the unwillingness of the internet infrastructure players to accept or bring in the changes that would allow or adopt to facilitate supporting these networking technologies or the newer disruptive technologies. And on the other end, when the scale of the network and the proprietary hardware and protocols started to build on, it made it even more worse to intervene and do any disruptive or progressive technological advancements and try it out on the internet testbed. And especially when we consider these monolithic routers, which were basically developed and built by proprietary implementations from various manufacturers, they built around the standardized protocols that they would support, and any other protocol if you'd want to bring and experiment, it was not open to experiment or even open to deploy and try. And this led to another form of ossification because of the market influence. And also, like we said, because of the different and middle boxes which were proprietary built devices, again, a new scale of the manufacturers would try to control what kind of protocols would work and what wouldn't. So ossification, to think of for those who are not familiar with the term, is a kind of a hardening. Like when our bones, when we are young, they are somewhat agile, but as we age out, they become hard, and the only way that they can be bent is brick. They would no more bend. And take, for example, the same with the wood. Like as the wood ages, we call that as a petrified wood. And this, when you try to break it, it would be like also fragile in the sense that it would completely break when you hit it, but not have any dents or bend around when you try to use it. So the state of this is exactly what happened with the internet. in the sense the protocols that they used to support, the functionalities that you would want to apply and exercise were all getting confined, and more they were getting aged and robust over, and it was not easy to tweak any of the aspects over the internet. And this is what we precisely termed as an internet impasse, because it would no more allow the researchers to try and experiment something new in the internet, and also not allow any new aspects to be brought in an easy fashion, even though there is a need to bring. To put an example, when the IPv6 it started in the late 90s, as of today we have nearly passed 2.5 decades. Still, we have not reached less than around 60% perforation of IPv6, and that's again due to kind of an ossification that we see around the IPv4 address space and unwillingness of many of the players to change to IPv6. And to look at it in another perspective, whenever there is a technology that grows and whenever there is a technology that is taken in terms of the services that it provides, we see there is a nice service infrastructure cycle which is fundamental for evolution of any of the technology, and it was the same with the networking. On one end, you would have the kind of network services that would grow up, and these kind of network services, as they grow and or a given network service, the demand for a kind of a network service increases, you would need to build the infrastructure to cater to those demands of newer network services and or the increased scale of network services that you would want to support. And that's exactly what the green box shows, where you are trying to build or upgrade your infrastructure to meet the service requirements and the scale requirements of the services that are provided over the internet. And this chain worked well up till the early 90s or the late 90s. And then we started to see that the networks that were built to accommodate certain services at an expected scale started to see a huge upsurge in the scale, and the services were no more able to be accommodated. And second, it also, like what the points that we discussed earlier, because the infrastructure grew to such a wide scale that making the changes became almost difficult, and it was not easy to make a change and adopt it at the scale of the network. And this cycle got stuck in the early 2000s, making many of the network researchers, network community think of the alternatives on how this impasse can be broken. And this, in a sense, led to what we call as the ossification, or the loss of flexibility, extensibility, and evolvability of the network. And it was argued by many that this ossification is a natural evolutionary stage in the development of highly successful technology, and internet just became a victim to it in the early 2000s. And these new amplifications or a significant increase in the scale of network usage often stresses the network infrastructure in a way that we are required to rethink of the current mechanisms, or a significant step increase in the network resources that we would need to accommodate if we have to break over this internet impasse. So to summarize, the internet evolved as an experimental packet-switched network, but grew beyond leaps and bounds with diverse protocols and services, and variety of the middle boxes started to take shape, and the network, as they grew, they became also resistant to the changes in terms of the protocols that you would want to put or adapt or change any aspects in the networking stack, and thus the networks became ossified. And in a sense, many aspects appear to be now set in stone, and typically you would hinge around the same set of network protocols, and it became very difficult to make any changes. And more so, this ossification is a serious concern, especially when we have a network that requires a lot of innovations, and especially when we have the network that is far from perfect. So whenever we have to devise and design solutions to fix those imperfections, we also need to bring those into effect, experiment out, and see how these can be brought out. But unfortunately, this ossification created an impasse for innovation. And interestingly, this problem is not unique to networking, but it is just that it is more severe when it comes to the networking, because the experimentation relies on having an open internet aspect where you could deploy and test. But unfortunately, there is no means now that you can make these changes and experiment out on an internet scale. And also, the market plays its own role in terms of the dominant players who dominate and lay the terms of what protocols need to be there and what cannot be supported, and it becomes very hard to change and also makes the progressions very slow. And these competitive environments often allow new entries in many ways, and they would be the barrier breakers. But when the scale of internet, it becomes really difficult to even respond to those newer competitive emergent aspects. Hence, the network, unlike the other domains, was less open to effective computation, and this made the problem even worse. So overall, what we would see is that there is a need to rethink about the networks, especially in terms of trying to have the researchers try out different aspects over these networks in a way that they could experiment, try out different innovations much more easily. So this demands to break the impasse and deossify the networks.